Okay, so today we're going to be discussing Chef Notes, problem code CL16BF if you want to access the link through that. Either way, so I'm going to be discussing the problem in short. The problem tells us that the chef lives in a city where the number of intersections and roads, and all the roads are one way. With this very interesting statement which they're given us is that for any two intersections A and B, once you travel from A to B, you can never return to A again because there's simply no route you can take to get back to A. So we'll think about what this means in due time. So the remainder of the problem is, so you're in an intersection A and you want to reach the intersection B. And you need to know you have to give the number of ways to do so, modulo 10 power 9 plus 7, as the answer could be exponential.
We're given n intersections. In graph terminology, that'll be a node. Let me increase the volume. And m edges, which is a road. Other way around, but no problem. This is unidirectional, which is important. And the constraints were n less than equal to 10 power 5, m less than equal to 10 power 5. So what we notice in the constraints is we need a linear or n log n or something, anything less than n squared, right? Okay. So they've given us an important statement. If you have a path from, I'm going to call them cities or nodes, from node A to B, there's no way to reach A from B. That is, B to A, not possible. Okay, so let's look at what this implies. So if I have a graph like this, A, B, C, and I come back to A. So that means if I want to reach A to C and come back to A, there's a cycle. Wait, let's do this a little bit. So what they're trying to imply is that there is no cycle in this graph. So the only way I could reach A from C is if I come from C to D to A, any predecessor of A in this graph, directed graph, or from C to A, and any path which I take would construct a cycle. If I go C to D, then I can D to A and A to C would be cycle, or C to A and A to C would be cycle. So they're just trying to tell us we have no cycle in this graph. So we have a special type of graph. It's directed plus no cycle. What this implies is it's a DAG, which is a directed acyclic graph. Okay. Now let's get to the problem itself. Now that we got that observation out of the way. So there's two ways of handling counting problems. Two common methods. One would be just get a mathematical formulation. And the second would be a DP solution. Here there doesn't seem to be any viable way to get a mathematical formulation because based on the graph, it's hard to say, but there is a DP solution. So let's figure it out. So so let's say you have A to B, B to C, A to C, C to D, and B to D. Okay. So the number of ways to reach D is what? Number of ways to reach D is equal to number of ways to reach B. Because if you have a path from the source to B, then you could just extend that path to B to D, right? And similarly, it's the number of ways to reach C. Because any path that terminates here, you could just extend it to C to D. So in general, what you notice is the number of ways to reach a node is the summation of the number of ways to reach a predecessor, right? I mean, a neighboring node. Such as if you want to reach D, it's like if you want to reach more formally, what we could write is dp of v, where dp of I is number of ways to reach I, node I, is dp of v is equal to sigma of dp of u, where there's an edge u to v. Okay, so we got that out of the way. So now there's two ways to compute this dp, right? One would be bottom up, second would be top down, any dp in fact. Okay, so let's discuss both the methods, though we're going to implement this one, right? So for the bottom up approach, so just look at any dp. What you need is linear ordering to compute the values. For example, if you want to compute the Fibonacci numbers, fib of n is equal to fib of n minus 1 plus fib of n minus 2. Look at 2. If you want to compute it, you need the values of 1 and 0. Look at 5. If you want to compute it, you need the values of 4 and 3. And for 4, you need 3 and 2. And for 2, you need 1 and 0, right? So this is strict ordering. This hierarchy, dependencies is a better word for it. So let's draw what I mean by dependencies. So for 5, I need 4 and I need a 3. 4, I need 3 and a 2. And if you look at it, you're just going to get another directed acyclic graph, right? And but the graph would look like 5 to 4 to 3 to 2 to 1. And 2 is going to, 2 is going to depend on 1, 3 is also going to depend on 1, 4 is dependent, and so on, right? So for this, we know the ordering in which we have to compute the values. The ordering we have to compute is 1, 2, 3, 4, 5. What this means in the dependency graph is, oh sorry, one second. Yeah, what this means in the dependency graph is you're always going to compute values which are in a certain order, such that such that you fill up all the dependencies which are the edges before you compute the node itself. So how you could do that in graph terminology is a topological sort of the graph. Toposort of the graph gives you a linear ordering for your DAG. So if you have a linear ordering, then I could just compute the DP in that order, right? So there is no real worry. There's multiple algorithms for Toposort if you're not familiar with it, which is just a variant of DFS or Khan's algorithm. The first is much easier to implement. Okay, so if we find this linear ordering, which is Toposort, our algorithm just consists of two steps. One is Toposort and the DP. Seems fairly straightforward. So that's all there is for the bottom case. Now let's look at the top-down case. So what happens for the top-down case is, so top-down is basically questioning each other, right? So if you want to reach 5 from 3 and 4 and this way, so let's say it parts from 2 to 5, right? So top-down essentially is that I'm starting from the destination from 5 and I'm going to ask 3, how many ways are there to reach you and how many ways are there to reach you 4, and let me add them up, right? And 3 is going to ask the same to this. So in a way, we're going from the top of this dependency graph to the bottom. So that is the difference. That's what top down and bottom up really means. And so let's look at how the algorithm is done. We first call the function on 5 asking how many ways, and he'll ask for 4 and 3, and he'll ask for 2, and so on. So in a way, all the dependencies are satisfied and we don't need to topos. Why does this work? The thing is, the recursion is doing the work for us. It's asking its dependencies. We don't have to explicitly solve it in that order. So I mean, essentially the same thing. The recursion is doing what we're trying to do, what the toposort is doing, but it's much easier to implement, right? Okay, so in this, let's write how the code would look. So if you want to compute f of x, you would go through all edges, and let's say your v actually, from v to u, where there's u to v, and just add them up, right? So total is equal to number of, so f of u sigma, and return total. Seems simple. So notice in this implementation, we need all edges from u to v when we're at f of v. So for that, we could, in our adjacency list, we'd reverse all the edges. So if we hold the reverses, then from v, I'd be able to go to its dependencies, even though the graph is modeled the other way, right? So that's how. So the more clarity will come in the code, but there's a few more subtleties in this which we'll discuss. First, let's get to the runtime. So in the bottom approach, toposort is OV plus E, as is just a modified version of the DFS. And the DP is also a linear algorithm. So both, you could say it's O of n, where n is the size of the graph. And in general, that means the number of vertices plus the number of edges. So similar here, the DP, it's going to visit every node once, and it's going to ask all its dependencies. So it's going to visit every edge once as well. Why does it visit every node once? Because we can just apply memoization. So even though that 3 has to be computed twice, once for 5, once for 4, we won't do that. Once 3 gets the answer once, we'll store its answer and we'll just return it. So it becomes an O of 1 operation. So this entire algorithm is also linear time. Okay. So there's only one subtlety in the implementation, which is they're asking us to print the answer modulo 10 power 9 plus 7, right? So this is just modular arithmetic. It's nothing really. So let's say the number of ways to reach, so if you want to compute a plus b mod m, right? That is the modulo of the entire answer. This could overflow. If you have 10 power, this is indeed correct, but if you have this as 10 power 10 and make this as 10 power 10, this would be 10 power 20 mod m, and you'd overflow there itself in the addition itself. So what a plus b mod m breaks down into is a mod m plus b mod m whole mod, and that's it. We'll look at the code now.
Okay, let's get to the code then. Let's save it. Give me a second, I'll just get all the input and then we'll get to the main code. Why I'm minusing? Because they've given us one base and I want zero based indexing. Now I need an adjacency list of n size, and for and I is n plus and u to v, c and u to v, and u. So for our recursion, I've said we need the edges in reverse order, though logically it is in correct order. So adjacency v dot pushback u. Okay, and so in solve, number of ways to reach int v is what? So however I define the recurrence, dp of v is equal to sigma of dp of u, where the base case is dp of u is equal to 1 already. dp of source is equal to 1. That's stupid. Okay. So the number of ways to reach v, note that we already also need to pass the adjacency matrix. So if v is equal to source, so let's make source as a global variable. Then what do we do? dp of v is equal to 1. dp of v is equal to 1 as dp of is equal to 0. I have not defined the DP array, and in DP of n constant equal to, so they've given us the constraints of 1e5. Okay, actually this is unnecessary as global variables are automatically declared as 0. Okay, so now for to x to adjacency of v, dp of v plus equal to solve of v comma adjacency. Now we could memorize this by actually, instead of using another array, let's actually set this as 0. Initially mem set dp as -1. So if dp of v not equal to -1, return dp of v. So we've just done some standard memorization, but if we've already visited, dp of v won't be -1, so we'll just return the value. If we've never visited before, we'll do the computation. Okay, so yeah, but this statement is wrong as well, as it's just a little subtlety in implementation. We need modular arithmetic. So let's define the mod, which they've given as 1e9 plus 7, and using modular arithmetic rules is equal to dp of v mod plus solve of x comma adjacency mod entire mod. Okay, so now we've got dp of v, and we should return this value. Cool. So now our answer was solve of destination, number of ways to reach destination, and adjacency matrix is this, and we should print this out. So let's go. So let's test this. Taking time. Oh, my bad. I've given file input without defining. Let me just chef enrolls. Let me end the process. Yeah. So one thing which I use is online judge hashtag and if. Okay, so for whoever's not familiar with this, what I'm trying to do here is I'm just going to take input through a file, and while submitting I don't really need to remove these input lines, as I'm saying if not defined online judge, and CodeChef compiles with this extension, so we're alright. So it's just a nice way to finish work, and it ran pretty correctly. Okay, then let's submit and test it. Right, submit. Okay. Yeah, and it works. So that's it for today. Thank you.